turbulence or boundary layer effects, skewing the results. Computational fluid dynamics, CFD. Simulations play a pivotal role in this phase of design. CFD simulations involve the use of advanced mathematical models and numerical methods to simulate the behavior of fluids, in this case, air, and the interaction of objects within them. Engineers use these simulations to predict how air will flow around and interact with the model in the wind tunnel test section, by tweaking variables like the shape and dimensions of the test section. They can optimize it to closely replicate real-world conditions. A critical consideration in designing the test section is the minimization of interference effects. Interference refers to any distortion or disruption in the airflow caused by the presence of the test model, supports, or other elements within the test section. Engineers aim to minimize interference to ensure that the data collected accurately represents the aerodynamic behavior of the model itself, rather than being influenced by the test section's structure. In some advanced wind tunnels, engineers go to great lengths to reduce interference. They may employ techniques such as boundary layer control, which involves using sophisticated suction or blowing systems to manipulate the airflow near the model's surface. This helps maintain a smoother, more uniform airflow and minimizes the impact of the boundary layer, which is the thin layer of slow-moving air near the surface of the model. Moreover, engineers also consider the type of airflow they want to create within the test section. Depending on the specific objectives of the experiments, the airflow may need to be steady and uniform, turbulent, or even include variations in temperature and pressure. The design of the test section and the air handling system must cater to these requirements. In essence, the test section of a wind tunnel is a critical area where engineering precision and attention to detail are paramount. Using CFD simulations and optimization techniques, engineers strive to create an environment that faithfully replicates real-world conditions while minimizing interference and other factors that could compromise the accuracy of the data collected. It's in this carefully designed and controlled space that breakthroughs in aerodynamics, aeronautics, and various other fields are made possible. Wind tunnels come in various shapes and sizes, from small, low-speed tunnels used for research and development to large supersonic and hypersonic facilities. Each type poses unique engineering challenges. Supersonic wind tunnels, for instance, must deal with the effects of shock waves, extreme temperatures, and high pressures. Engineers must employ advanced materials and cooling techniques to withstand these conditions. Supersonic wind tunnels are a prime example of how engineering ingenuity must contend with extreme conditions. These facilities are designed to replicate the high-speed flight conditions experienced by aircraft and spacecraft, where the velocity of airflow exceeds the speed of sound. In this regime, engineers face a multitude of unique challenges. One of the most significant challenges in supersonic wind tunnel engineering is the management of shock waves. As objects travel through the air at supersonic speeds, shock waves form, causing abrupt changes in air pressure, temperature, and density. These shock waves can interfere with the accuracy of experiments and measurements. Engineers must carefully design the test section, nozzles, and diffusers to control and minimize the impact of these shock waves. Computational fluid dynamics, CFD, simulations are often employed to optimize these components for efficient supersonic airflow. Furthermore, the extreme temperatures generated during supersonic testing demand sophisticated solutions. As air molecules are compressed at high speeds, they release heat energy, resulting in elevated temperatures within the wind tunnel. Engineers must select materials that can withstand these extreme conditions without deformation or degradation. Advanced alloys and composite materials with exceptional heat resistance are commonly used. Additionally, cooling systems may be integrated into the wind tunnel infrastructure to ensure that the test section remains at the desired temperature, preventing any adverse effects on the models being tested. Another crucial aspect of supersonic wind tunnel engineering is managing high pressures. The high